Imagine you are holding a massive 500-page book, and you need to know the exact page count for a project you're working on.
Right, which is already a pretty tedious task.
Totally. So you sit down, you manually flip through every single page all the way to the end, and you count 500. Then you close the book.
Okay, simple enough.
But then, to execute the very next step in your project, you need that exact page count again.
Oh, I see where this is going.
Yeah. So instead of just remembering the number you just arrived at, you open the book back up and you manually flip through all 500 pages a second time.
I mean, it sounds completely absurd, right?
Right. No rational person would operate that way. But the reality is, the software running on your devices right now, and very likely the daily workflows you rely on, are doing the exact equivalent of that thousands of times a day.
And the fascinating thing is that these inefficiencies, they usually aren't the result of broken systems.
No.
Not at all. They are a byproduct of systems that actually work, but have this hidden invisible drag.
Yeah, that invisible drag is exactly what we're getting into today. Welcome to the deep dive, everyone.
Glad to be here. To really explore this concept, I want you to picture a workspace that is ruthlessly optimized.
Like minimalist desk, perfectly organized.
Exactly. Or maybe a cascading monitor displaying incredibly clean, structurally perfect code. That is the visual space we are in for today's deep dive because we are looking at a true masterclass in stripping away the unnecessary.
It really is a masterclass. So the source material we're pulling from today is a blog post dated May 28, 2026.
Yeah, written by a programmer named Eng.
Right, Eng. And the title is Efficiency Refactoring in Haskell String Processing. It actually comes from a larger series. Eng writes specifically Notes on Haskell Programming, Part 147.
Part 147. That is a lot of notes.
It's some serious dedication. Now, I want to say right up front, if you are a software engineer, do not tune out.
Oh, absolutely not. The lessons here apply to everyone.
Exactly. While we are going to get into the actual mechanics of how computer memory works, the core theme of Eng's post is universally applicable.
It's really about how a microscopic change in the structure of a process can literally cut the required effort in half.
Yeah, the art of refactoring. Looking at a process you've already built, acknowledging that it succeeds in its primary goal, but realizing it is, wasting energy to get there.
Right. It works, but it works too hard.
So let's get right into the specific puzzle Eng is trying to solve. Eng is working on a function called summarize.
Okay, the summarize function.
Yeah, and the goal of this function is to take a piece of text, which is formatted in the Haskell programming language, as a specific data type called text.
Capital T, text.
Right, and it needs to convert it into a different format, which is a string type.
Which seem like the same thing to a layperson, but we'll get into why they aren't.
We definitely will. But there's a rule applied to this conversion first. The code has to check if the length of the text is 20 characters or shorter.
Which seems like a simple enough gateway, right? It's just a basic if-then scenario.
Exactly. So in the original version of the code, the logic tells the computer to check if the length of the text is less than or equal to 20.
Okay.
If it is, the code executes one path. But if it isn't, which Eng refers to as hitting the otherwise block, the code has to do something else entirely.
And here is where Eng discovered that hidden drag we talked about.
Yes, because to figure out what to do in that otherwise block, the original code called the length function all over again.
It was double dipping.
Literally double dipping. It asked a question, got the answer, threw the answer away, and then immediately asked the exact same question.
It's the book analogy perfectly. Reading the whole book to count the pages twice.
It is. But I want to push back on this a little bit.
Go for it.
Because I think a lot of people listening might be thinking about the raw power of modern hardware.
Sure.
In the age of super fast processors that can execute like billions of instructions per second, does asking a CPU to check the length of a string twice actually matter?
That's a fair question.
Right. If it takes a fraction of a nanosecond, isn't Eng just being a bit, overly fastidious here?
That is the natural counter-argument. And, if we were only ever dealing with a 20-character word, you'd be totally right.
But we aren't always dealing with short words.
Exactly. Eng specifically points out that this double dip transforms the calculation from what's called an O of n operation into an O of 2n operation.
Okay, big O notation. That's how computer scientists measure the scalability of an algorithm, right?
Right. It describes how the processing time grows as the size of the input grows. And to understand why O of 2n is so toxic to performance, we have to look at what checking the length of a string actually requires the computer to do mechanically.
Okay, let's break down those mechanics because, when I highlight a paragraph in a document and click word count, it feels instantaneous to me.
Oh,
The
totally.
computer just seems to magically know the length.
It feels like magic, but it is a very physical process happening inside the computer's memory.
How so?
Well, in Big O notation, the letter n represents the number of elements the computer has to process. In this case, n is the number of characters in the string.
Got it.
And in many programming environments, the computer doesn't inherently store the length of a string as a piece of metadata that it can just, glance at.
Wait, really? It
Yeah.
doesn't just keep a tally?
Not always, no. To find the length, the processor has to start at the memory address of the very first character, and it has to literally walk down the line.
So it's counting them one by one.
Exactly, one by one until it hits a termination signal that basically says, hey, the string is over.
Wow. So it's essentially walking down a long hallway and counting every single door.
That's a perfect analogy. If the string has 5 characters, n is 5, the computer takes 5 steps.
Okay, that's fast.
Right. But what if that string is a massive data set? What if n is 5 million characters?
Oh.
Yeah. The computer has to take 5 million individual steps through its memory to find that termination signal.
Which means an O of 2n operation is the computer walking those 5 million steps, getting the answer, throwing the answer in the trash, and then walking the exact same 5 million steps a second time.
Yes. 10 million steps to answer a question it had already solved at step 5 million.
That is wild.
So to answer your pushback at a small scale, you don't notice it. But at scale, that redundant traversal creates a massive bottleneck.
Because it's just doing pointless work.
Exactly. The CPU is burning cycles, generating heat, and taking up time just retreading ground. It is the literal definition of wasted computational energy.
Okay, that makes a lot of sense.
Right.
The inefficiency doesn't just scale linearly in terms of impact. It really compounds the drag on the whole system.
Precisely.
So how does Ang actually fix it? Because the solution isn't to write some, complex new algorithm, right?
No, it's incredibly simple. It's entirely structural.
Yeah, at the very bottom of the code block, Ang introduces a where clause.
A very elegant solution.
They just write len equals length, txt.
Mm-hmm.
And then up in the actual logic, instead of running the command to check the length again, the code just checks if len is less than or equal to 20.
It's a brilliant pivot because it fundamentally shifts how the program interacts with its data.
How so?
Well, instead of issuing a command to constantly perform a task, Ang is declaring a fact.
Oh, I like that. It reminds me of assigning an assistant to count the pages of that massive book.
Right.
The assistant counts the 500 pages once, writes 500 on a brightly colored sticky note, and slaps it on your desk.
Mm-hmm.
They name that sticky note len.
Mm-hmm.
Now, anytime your process requires you to know the length, you don't open the book. You just glance at the sticky note.
Exactly.
But let me be devil's advocate again here for a second.
Bring it on.
Doesn't that sticky note take up physical space on your desk? In computer terms, aren't we just trading processing time for memory consumption?
Yes, we are.
Because you have to store that new variable somewhere in the RAM.
Right. You're touching on one of the most fundamental concepts in computer science there, the space-time trade-off.
Space-time trade-off, okay.
You are absolutely right that we are trading space for time. We are allocating a tiny bit of memory to store that integer, but you really have to weigh the relative costs.
Right, the scale of it.
Yeah, storing a single integer like the number 500 takes a minuscule fixed amount of memory. It's usually just 64 bits in a modern system.
So basically nothing.
It takes up essentially 0 space. Contrast that microscopic memory footprint with the massive processing cost of traversing millions of characters again.
Wow, okay.
The cost of storing the sticky note is entirely negligible compared to the cost of rereading the entire book.
So an incredibly cheap trade.
Unbelievably cheap. And Ang explicitly notes in the post that this change makes the code much cleaner.
Cleaner, yeah.
They aren't just talking about the execution speed, they're talking about the structural purity of the code itself.
Right.
In functional programming languages like Haskell, there is a strong emphasis on declarative logic. By moving the calculation to a where clause, you are making a definitive statement.
Like setting a rule.
Exactly. You're saying the length of this text is a universal truth for this block of code, and we only need to discover it once.
I love that framing. You are establishing a universal truth. You are taking away the uncertainty and all that redundant labor.
Yes.
And establishing that truth is actually what allows Ang to tackle the second half of this refactoring journey.
Because the job isn't done yet.
Right, because once the length issue is solved, the text still has to be converted. The summarize function still has to actually turn that text type into a string type.
Which brings us to the second optimization.
Yes. Ang notes that they also, quote, refactored the code to remove the duplicated unpack calls.
Unpack calls, Rob.
In the older version of the code, Ang was unpacking the start strings and the end strings individually. And to really grasp why this was inefficient, we need to understand what unpacking actually means in this environment.
It's a very specific operation.
Yeah. You mentioned earlier that text and string are different data types in Haskell.
They are, and understanding the difference between them is critical to understanding why Ang's second fix is so powerful.
Let's get into that.
In Haskell, a string and text aren't just two different names for the same thing. They are fundamentally different ways of organizing data inside the computer's physical memory.
Okay, break that down for us. How are they structured differently under the hood?
Let's start with a string. In Haskell, a string is essentially a linked list of characters.
A linked list?
Yeah, think of a linked list like a sprawling scavenger hunt.
Okay.
The first letter of your word is written on a piece of paper. At the bottom of that paper is a clue, a pointer that tells the computer the exact physical address in the RAM where it can find the second letter.
Wait, so they aren't stored together?
No. The second letter might be in a completely different sector of memory entirely.
Oh, wow.
So to read a string, the computer is constantly jumping around, following pointers from one node to the next.
That sounds incredibly fragmented. It must take up a lot of extra memory just storing all those pointers.
It takes up a massive amount of memory, and it's slow to traverse because the data isn't grouped together.
Right, you're constantly following clues.
Exactly. But it is very flexible if you need to manipulate individual pieces of it.
Okay, so that's a string. What about text?
Text, on the other hand, is the complete opposite. Text is a contiguous array.
Really?
It is a solid, tightly packed block of memory. All the letters are sitting right next to each other in a perfect row.
Oh, nice.
There are no pointers, no scavenger hunt. It is highly optimized and very fast to read.
Ah, okay. So when Ang says they are using an unpack function to convert text to a string,
Yeah.
the computer isn't just changing a label on a file. It's physically walking through that highly efficient, tightly packed array, ripping it apart and blowing it up into a sprawling, scattered linked list.
Exactly. It has to allocate new memory for every single character and create a new pointer for every single node.
Wow.
Unpacking is a massive memory allocation chore.
It's kind of like paying a hefty computational delivery fee.
That's a great way to put it.
Right. Because if you unpack the start string individually, the computer has to spin up all that memory allocation machinery, pay the fee, and build a linked list. Then, if you unpack the end string separately, it has to spin up the machinery and pay that massive fee a second time.
Precisely. You are forcing the machine to do the heavy lifting twice, which is why Ang's new method changes the sequence of operations.
What do they do instead?
Instead of unpacking them individually, Ang writes, we now concatenate them first and then unpack the entire result just once.
Concatenation just means joining them together, right?
Right. While the start string and the end string are still in that highly efficient, tightly packed text format, Ang joins them into one single solid block.
Going back to the delivery fee idea, concatenation is like putting all your items into the same shopping cart before you check out.
Exactly.
By joining the text first, you only force the computer to initialize that expensive unpacking process one time. You push the combined block through the machine, and you only pay the computational transaction fee once.
It perfectly mirrors the exact same philosophy as the first fix with the length check.
It really does.
Both of these optimizations are about identifying structural repetition and consolidating it.
Yeah.
Don't traverse the string twice to find its length. Do it once and declare it as a fact. Don't allocate memory for a scattered linked list twice. Join your data together and allocate the memory once.
All about grouping the heavy lifting.
Exactly. And Ang sums this up beautifully at the end of the post. They validate the whole exercise by writing, "They're small changes, but definitely effective ones."
I think that realization is so important.
It really is. Critical thinking, especially in technical fields, isn't always about inventing a brand new, groundbreaking algorithm from scratch.
Right. Sometimes it's much simpler.
Often, it is just about having the patience and the discipline to look at the system you've already built and noticing where it's tripping over its own feet.
It's about looking at your own work objectively. You don't have to write new code. Sometimes you just have to rearrange the sequence of what you already have.
Yes, exactly.
We took a tiny snippet of notes from a programming diary from May 2026 and found a complete blueprint for how to build better systems.
And that blueprint is entirely applicable outside the realm of Haskell or software engineering.
Oh, absolutely.
Think about how you operate in your own daily life. The mindset Aang demonstrates here is a universal shortcut to being highly effective.
Yeah, whether you are prepping for a major presentation, outlining a complex legal brief, or trying to organize the workflow for an entire department.
If you step back and look at your process, you will almost certainly spot an O of 2N redundancy.
A place where you or your team are doing the exact same labor twice.
Exactly. You are rereading the book to count the pages again.
And when you find that, you can restructure it. Find your version of the where clause.
Right. Calculate the hard thing once.
Put it on a sticky note, establish it as a universal fact for your team, and just reference that note from then on.
Concatenate your tasks before you execute them.
It is how you become drastically more efficient without actually having to work any harder.
You aren't working harder, you are just working cleaner.
Which leaves us with a final lingering thought for you to chew on as you go about the rest of your day.
Always love these.
Think about Aang's perspective for a moment. Aang is clearly a highly dedicated, experienced programmer.
Without a doubt.
This blog post was titled, Notes on Haskell Programming, Part 147.
Part 147.
Right. They have been analyzing, writing, and thinking about this specific language for a long, long time. And yet, even at Part 147, Aang is still discovering hidden redundant double dips hiding in plain sight within their own code.
It's a continuous process of refinement.
It really is. So the question for you is this. If someone that experienced is still uncovering invisible inefficiencies in their highly specialized work, how many invisible double dips are currently lurking in the workflows, the habits, and the processes that you rely on every single day, just waiting to be concatenated, unpacked, and finally streamlined?
That is the real puzzle we all have to solve.
It absolutely is. Thank you for coming along on this deep dive. We will catch you next time.